So this is revision of the AQA forces topic. Now the thing about forces is they are measured in the Newton, and there are really two different sorts. We have contact forces and non-contact forces. So contact forces are where you have two surfaces in contact. So we're talking about friction, air resistance or drag. You've got the tension, which is maybe when something is being pulled, like a spring. And then normal contact force, I'll come on to in a little bit of time. Non-contact forces, they can act over a distance. So we might talk about the gravitational attraction between two masses. Maybe if you've got a negative and a positively charged object, you've got some electrostatic force or the magnetic force as well. Now the thing about forces is that these are vectors. And a vector is something that has size and direction. And what that means is we can then represent a force with an arrow, where the length of the arrow tells you about the size of the force, and the way the arrow pointing is telling you about the direction. That's different to a scalar quantity, which only has size. Now, something that often causes confusion is the difference between mass and weight. And weight is a force, and that's caused by the mass of an object in a gravitational field. So like I said, we always measure our weight in newtons, we measure our mass in kilograms, and that means that the gravitational field strength is measured in newtons per kilogram. And this field strength really depends about which object we're considering. On the moon, for example, it's about 1.6 newtons per kilogram. On Earth, it's about 9.8 newtons per kilogram. So if you need to convert from kilograms into newtons, you just multiply by 9.8. Now, in order to actually measure the weight of an object, what we can use is a Newton meter. Whereas I suppose, strictly speaking, if you want to look at the mass of an object, we should use a mass balance. And that would then give you a value, often in grams or kilograms. And you've got to remember as well that the weight of an object, this acts at the centre of mass. Now the thing about forces is that if we have an object, which I've just got here, and maybe there's a 5 Newton force acting to the left, and a 10 Newton force acting to the right, what we can do is we can replace both of these arrows with a single arrow to show the overall force acting on the object. Now if you've got 10 Newtons that way, and 5 Newtons that way, that means overall there's going to be a 5 Newton force acting to the right. And this is what we call the resultant force. And this is really useful if we think about real objects. Perhaps we just have an apple which is just sat on the desk here. At the moment it's not moving, and that means there's going to be a balanced overall force. What we can do is we can maybe draw a diagram of the same thing. So this is my apple, and what we might find is that there's a force acting down. In this case it would be the weight of the object. And then there's another force which is an equal size arrow but in the opposite direction, and this one here fits this is now the force of the desk pushing back, and that's what we call our normal contact force. Now if we had another object which maybe had a force in this direction and a force down here, we can again look at the overall force, and what we can do then is add up these two vectors together. And effectively, if I just put in a line like this, the resultant force of these two arrows, because there's one to the right and one which is down, is going to be to the right and down. So this again is another way of showing that resultant force. And because it's a vector, we're also often interested in the angle that force is acting in. So it's not just the size of the resultant force, it's also the direction that it's acting in. Something we can do which is similar to this is maybe we had a force acting at a certain angle, I'm going to call that theta. We can also resolve this force into its vertical and horizontal components. So if there's a force which is acting up and to the right, effectively there's a size of a force acting upwards and a certain size of force acting to the right. And we can see again how the length of the arrow to the right is the same as the size of how much that arrow there goes to the right. Hopefully that makes sense. I will have some more videos that explain this in a little bit more detail. But drawing diagrams is a really useful way of maybe looking at all the forces on the object, finding out the resultant force, and then finding the size and the direction of that resultant force. Now the other thing about forces is if we have an object and we apply a force to it over a certain distance, we're then doing work. So this thing here, work, is quite an important concept. And if you want to look at the work done on an object, I'm going to call that W, so this is the work done, that's equal to the force applied multiplied by the distance that it goes. So in the case of moving this Lego block, we need to think about how far it's travelled in the direction of the force and the size of the force. Now, work done and energy transferred are both measured in joules, we've got our force measured in newtons and our displacement, the distance that it travels in the direction of the force, is measured in meters. And this then gives us the definition of what 1 joule is. So 1 joule is the work done when a force of 1 newton causes a displacement of 1 meter. The next thing we're going to look at is forces and elasticity. And basically this might be when you're bending, you're compressing or you're stretching an object, and especially the normal kind of standard spring that we have here. Now, if it's elastic, it means it goes back to its original shape when the force has been taken off. However, something which is inelastic, perhaps a spring that is bent too much, it doesn't return to its original shape, and then it's not elastic anymore. It's inelastic, or we can also call that plastic. Now for that spring, the force applied is going to be proportional to the extension of it. Extension means how much longer it's got. In fact, there's an equation that we use which says that force is equal to K times E. So again, we measure our force in newtons, our extension in meters, and this then gives what we call the spring stiffness. That has the units of newtons per meter. Now that's the amount of force required to extend something, but if you do extend something, that spring can then store some energy in the elastic potential store. And we can also look at the equation that says the elastic energy stored is equal to a half Ke squared. So this really depends on how stiff that spring is and how much it's been extended. So again, this one is a force which is measured in newtons, but this is the energy stored measured in joules. Now, if you apply a force at a distance from an axle, you can then cause some rotation, perhaps the wheels of a car or maybe the steering wheel inside. And what we can then consider are moments, levers and gears. Now, the turning effect of a force is what we call the moment, and it's basically equal to the force multiplied by the perpendicular distance. That's important, the word perpendicular, distance from the pivot to the line of action of the force. So what we're saying here is that the moment, which is capital M, is equal to the force times distance. And here I'm going to use d for distance to show it's that distance from the axis. Now, because we measure force in newtons and our distance in meters, this gives our moment in the unit of the Newton meter. That's very different to the newtons per meter that we have for our spring constant over here. Now, if you have an object which isn't rotating but it's balanced, what we can then say is that the moments which are going clockwise are equal to the anti-clockwise moments. And if I just put that in shorthand over here, we can say that the clockwise moments are equal to the anti-clockwise moments if it's balanced. Now, in the simplest example, you have some kind of seesaw. If you know that there's a certain force at a distance, maybe going anti-clockwise, and you know the size of the force that you can apply, you can then work out the distance that you need to apply that force to make sure that this thing here is in equilibrium, it's balanced, and it's not rotating. Something that we also need to consider is pressure, and this is the pressure in fluids, so it could be things like gases or liquids. Now, to calculate the pressure at the surface of the fluid, that pressure, which is small p, is the amount of force per unit area. Now, by convention, we measure our force in newtons, our area in square meters, and that means the units for pressure are newtons per square meter, but we can also use another unit, which is a Pascal. That's capital P, small a. So if we're using our force in newtons, area in meters squared, we can then also give our pressure in pascals. For example, atmospheric pressure, the kind of pressure of the air which is surrounding you and me at the moment, is 101 kilopascals. So when it comes to pressure, we often have very big numbers. Now we can also think about the pressure in a column of liquid. Now really, the deeper you go down, so the greater the height that you go under the surface, the more water there is going to be above you, which is pushing you down. So as you go deeper and deeper, the pressure increases. It also depends upon which liquid you have. Water isn't particularly dense. If you had a column of mercury instead, because there's more stuff in a certain volume, the density of that material also affects the pressure that you're going to feel. And finally, it really depends upon where you are in the galaxy. If you went to Jupiter, or one of these big planets with a bigger gravitational field strength, you'd also then get a greater pressure as you went under. So we can say that the pressure is equal to rho GH. So the pressure depends upon the density, the gravitational field strength, and the height. Density is measured in kilograms per cubic meter. Gravitational field strength is newtons per kilogram. The height is in meters. And again, the density, hopefully you can see this, is measured in pascals. Now, if you submerge an object in this liquid here, there's going to be a force acting upwards on it. This is called upthrust, and it's because there's a difference in the pressure at the top and the bottom of that object. And this is the reason that things like ships, for example, they still float in water. So upthrust, or buoyancy, is a force that acts in a liquid or a fluid on objects. So I'm beginning to run out of room, so let's go onto this page here. The final thing is atmospheric pressure. Now, the atmosphere is basically above the Earth's surface, so this is supposed to be the Earth down here. There's a very thin layer of gas. Now, as you go higher and higher, the density of this decreases. Now, because pressure is caused by the impact of these particles on the surface, if you've got less particles impacting, that means as you go higher and higher, we go from a high pressure down here, and as you go higher and higher, the pressure gets smaller and smaller. Now, the next thing to consider is motion of objects. Now, we've already heard that there are scalar quantities which just have size, and also vector quantities that have a size and direction. Now, a good example of a scalar quantity is speed. So speed is just how quickly something is travelling. And these are just some of the speeds of everyday objects. So if you're walking along, it means that you're going at 1.5 metres per second. So every second you go another 1.5 metres. You also maybe need to think about things like the speed of sound, which is much quicker. So sound travels at 330 metres per second, depending on kind of exactly where you are in terms of the atmospheric conditions. But things like light and other electromagnetic waves, they travel at 300,000 metres per second, so even quicker than that. Now, scalar quantities also include things like distance, but there's a vector equivalent called displacement. And this includes not just the distance that something is moved, but also how far the direction that it's moved from its start point. So vectors always have a direction as well. Another vector quantity, a bit like speed, is velocity. And at GCSE, we define velocity of an object as the speed in a given direction. And we can also look at how quickly this velocity changes, which is then our acceleration. Now, looking at the relationship between distance and speed, we can say that s is equal to vt. Now, this is confusing. We don't use the letter s for speed. That's just something that we don't do. Instead, we use the letter v to represent speed or velocity, and this is measured in metres per second. S actually stands for our displacement. So think about the s for displacement, or the s in distance. So s is our distance in metres, and then time is in seconds. Now, another more useful way of looking at this equation is that v is equal to s divided by t. So the speed is equal to the distance divided by the time taken. And if you want to work out how quickly something is going, you simply need to measure the distance that something's gone and then time how long it takes to go that distance. Now, there's one little interesting thing about velocity if you're doing the physics, and that basically means that you can have something where something's velocity might be changing, but its speed stays constant. And this is where you've got something which is moving in a circle. So maybe you've got an object and it's rotating in a circle. It might be going 5 metres per second, so it might have the constant speed, but its direction is constantly changing. So sometimes it's going left, sometimes it's going down, sometimes it's going right, and then sometimes it's going up. So when you've got circular motion, this is a special case where you've got an object which has a constant speed but a changing velocity. Now, something which it's really useful to do is to draw different graphs to represent an object which is moving. Now, one of these is called a distance time graph. So we measure our distance in metres up here, and we have our time in seconds along the bottom. And what we might then do is plot some data for an object, and we can see how its distance changes with time. Now, on this graph here, the gradient of that line is equal to how quickly the distance changes per second. And that means the gradient is equal to our speed, v. Sometimes, however, you might get a curvy line, and then in order to work out the speed of that object or the velocity of that object from this line here, what you then do is you draw a tangent to that line. Once you've drawn a tangent to that line at the point that you're interested in, you can then measure the gradient by looking at the change in y and the change in x values, so you can actually then work out the value of the speed on this curved line. Another type of graph which is really useful is a VT graph. So this is our speed in metres per second, we've got our time in seconds here, and again what we can then look at is maybe how an object's velocity changes over time. Now for this graph here, the gradient is going to be equal to the rate of change of velocity. We're looking at how quickly that velocity changes per second, and that means our gradient is then equal to our acceleration. And actually, the equation that we can use to work out the acceleration of an object is equal to the change in velocity divided by time taken. So for this, we measure our velocity in meters per second, our time in seconds, and that means our acceleration then is the amount of meters per second per second. So the units for acceleration are meters per second squared. And we can often find that from a VT graph by looking at the gradient. And if we actually look at the area under this VT graph here, the area is equal to the velocity times the time, which we saw over here. The velocity times the time is equal to the distance travelled. So under a velocity time graph, the area is equal to the displacement. Now when we look at the change in velocity, what we're really looking at is the difference between the final velocity, which is v, and the initial velocity, which is u. So we can also say that this change in velocity is equal to v minus u. But now we can actually introduce another equation which says that v squared minus u squared is equal to 2as. So this one here looks a little bit confusing. Effectively, this is our final velocity in meters per second. Take away our initial velocity in meters per second. Often this is just zero in lots of equations that you might, or questions that you might be given. A is our acceleration in meters per second squared, and then our time here is in seconds. Sorry, our distance is measured in meters. So if you get a question and you can identify what you know from the question, you can often decide which equation you can then use to work out your final answer. Now, if you had an object which starts falling, initially it's going to accelerate quite quickly and it's going to get faster and faster. Now, for the apple falling towards the ground, there's going to be a constant downwards force called weight, and this doesn't change. But its air resistance increases as this gets faster and faster. In fact, if we were to plot a graph, a velocity time graph of the motion of a falling object under gravity, especially where you've got air resistance, we find that the graph does something like this. Now, the reason for this is that it gets to a point where its velocity doesn't get any quicker. And this point here is where the object has reached terminal velocity. And when the object is travelling at terminal velocity, there's no resultant force, so the weight in this case is going to be equal to the air resistance. I'm just going to put that AR for air resistance. That means there's no net force in it and it doesn't get any quicker. Now, there are 3 Newton's laws that you need to remember. Now, Newton's first law basically says that if there's the resultant force acting on an object is 0, so there's no resultant force in it, then stationary objects remain stationary, but things which are moving continue to move at the same velocity. So, for example, if you've got a racing car which is travelling as fast as it possibly can down a nice straight road, there's going to be a point where the air resistance is equal to the thrust of the engine and it doesn't get any faster. We then have Newton's second law. Now basically this says if there is a resultant force on an object, then the object is going to accelerate. And the size of that acceleration really depends upon the mass of the object and also the force that's being applied. So we can often write this as F equals ma. Now this is just the equation form of Newton's second law. So we've got our force in newtons, our mass in kilograms, and our acceleration in meters per second squared. And again, just to say that the acceleration of an object is proportional to the resultant force in it. So you get a bigger acceleration for a bigger force, and it's inversely proportional to the mass of the object. So that means that you get a smaller acceleration when you have a bigger mass for a certain force that's been applied. And then finally, we've also got, to complete the set, Newton's third law. And this simply states that whenever 2 objects interact, the forces they exert on each other are equal and opposite. So what that means is if we have the moon, for example, and this is being attracted to the Earth at the moment, the force of the attraction of the Earth on the moon is the same as the force of attraction of the moon on the Earth. And what we then have are a force pair. So that's Newton's third law. So a way to think about this is that if the force is equal to 0, then objects which initially had no velocity stay at 0. Objects that were moving still keep moving at a constant velocity. Here, if there is a force, then that force is going to be causing an acceleration. And here, what we're saying is that if you've got an object A and an object B, the force that they exert on each other are going to be equal and opposite. And here the mass is what we often call the inertial mass. And that's basically because things which are still want to stay still and things which are moving want to stay moving. And this inertial mass is basically their resistance to wanting to change what they're doing. And if we want to define inertial mass, then we pretty much define it as the ratio of force to acceleration for an object. Now I've pretty much run out of room again, so let's continue this on the page below. So the next thing we need to look at is the stopping distance for a vehicle. Now this is basically the total distance that a vehicle travels, which includes the driver's reaction time when they're thinking about and actually reacting to something they might see ahead, and then the distance that the car then, or the vehicle then takes to stop. So this is your stopping distance. Now the thinking distance is going to be affected by things of the driver. So this might include things like tiredness, by alcohol, by drugs, both legal and illegal, and also things like distractions, including mobile phones. So that's what's going to affect how quickly the driver reacts. But once they put the brakes on, that factors that affect how their braking distance might be applied, might be changed, include the condition of the roads. So it could be something which is maybe wet or icy. We're thinking about the condition of the tyres and the brakes. And of course, these and the total stopping distance are also going to be affected by how quickly that car is going. Pretty simply, the faster you're going, the bigger the stopping distance is going to be. And if we think back to the energy topic, the reason that a vehicle is slowing down is because there's a couple of brake pads which go onto the brake inside the wheel. And what this is doing is then transferring some of the initial kinetic energy store of the car into the thermal energy store of the brakes, which get hotter, and also the surroundings, which heat up as well. Something we also look at is momentum. And momentum is simply defined as the mass times the velocity. So momentum, confusingly, has the symbol little p for momentum from the word impetus, and this is equal to mass times velocity. Now for this, we measure our mass in kilograms, our velocity in meters per second, and that means the unit for momentum are kilograms meters per second. Now this is also a vector quantity, because it really depends on the direction that you're going, and you might have maybe a positive momentum or even a negative momentum. And it's really important that you try not to get momentum confused with kinetic energy, which also depends on the mass and the velocity of an object, but that then has a unit of joules. Now, in a closed system, what we can say is that the total momentum before an event is equal to the total momentum afterwards. So what we can say is that the momentum before is equal to the momentum afterwards. Now, if you're doing the full GCSE physics, you might need to do some calculations as well. So perhaps you had an object which is travelling along and it hits a stationary object and the two things move off together. If you know the total momentum of that moving object at the start, you can then work out the total momentum of the two things that move off together. So it might be that you're looking at the mass of an object times its initial velocity, and this is then going to be equal to the total mass times the combined velocity at the end. So this is where it's worth spending a bit of time doing some calculations and actually practicing a few questions about this. Now, the other thing is that we've already seen the equation from Newton's second law that F equals ma, and also that a is equal to the change in velocity divided by time. So what I'm going to do is combine these two together, and I'm going to replace this a with this term over here. So we can then say that F is equal to m times the change in velocity divided by the time. And if you've got the mass times the change in velocity, then this is also then equal to the change in momentum. So we can then say that the force is equal to the change in momentum divided by time. And what this basically says is that the force is equal to the rate of change of momentum. So what this means is that if you had a collision or something or an impact, if you change the momentum of an object more slowly, less force is going to be felt by that object. So this is why we have crumple zones on cars, it's why we have airbags, it's why we have soft pillows. Because what you're doing is you're still changing that momentum of the object, you're still slowing it down, but if you slow it down slower, it's going to experience less force. And that then means that there's going to be a less effect on maybe people involved in real life scenarios. And finally, that's it. We've done all of the forces topic for AQA GCSE. It's been a big one. Hopefully there's been something here which has been useful. Thanks for watching. So this is revision of the AQA waves topic. Now what waves do is that they transfer energy. And there are really two different classifications of waves. We have longitudinal and transverse. Now these longitudinal waves, what they have are the particles in the wave. These are vibrating maybe back and forwards in the same direction that the energy is being transferred. So if energy is being transferred this way, the particles are just going backwards and forwards. In a transverse wave though, the particles are going side to side and the energy is being transferred at 90 degrees. And examples of a longitudinal wave might include things like sound and ultrasound, but for a transverse wave we have the whole of the electromagnetic spectrum. So that includes things like light, and we're going to come on to that very soon, but also we have things like the water ripples on the surface of water. Now, if we were to look at the position of a load of particles along a certain bit of something which is vibrating, there's a wave travelling, what we can look at is the distance of the particles from their rest position. And this distance here is what we know as the amplitude. Okay, and so amplitude is the distance between where the particle normally is and how far it vibrates up and down. There's also a distance which is one complete wave cycle, and this is known as the wavelength. And we give the wavelength the symbol lambda, which is a Greek letter, a bit like an upside down Y, and this represents our wavelength. So we define the amplitude of a wave as the maximum displacement of a point on the wave away from its undisturbed position, while the wavelength is the distance from a point on one wave to the equivalent point on the adjacent wave. So it could be peak to peak, could be trough to trough, or maybe this point to this point. Now if we think about a wave, there's a link between how long it takes for each wave and the amount of waves per second. So the amount of waves per second is a frequency. So we can see now that there's a quicker, higher frequency here, but each wave takes less time. And what we can look then is the link between the time period for a wave and the frequency. We find that the time period of a wave is equal to 1 divided by the frequency. Now for this, we measure our time period in seconds, and it's capital T for time period, and we measure our frequency, which is the number of cycles per second, in hertz. So that frequency of a wave is the number of waves passing a point each second. The other equation that is really important to know is known as the wave speed equation, and this says that V is equal to F times lambda. So V is our wave speed. This is measured in meters per second because it's just the speed. We measure our frequency in hertz, and the wavelength, because it's a length, is measured in meters. And with this information here, it allows us to maybe look at things if we're measuring real waves. It might be as simple as we're measuring the speed of sound, where what you have is maybe two people who are a certain distance apart, and you can make a signal between these two people, and if you know the distance between them, which is S, maybe they make a signal and they record the signal that person's doing. Maybe they're clapping their hands or bursting a balloon. They can actually time the time it takes for that sound wave to get to them. And then you should remember that the speed is equal to the distance divided by time. Now you can do something similar with maybe a water wave in the tank. Maybe if you knew how the wavelength of that and you knew the frequency, you could then work out the speed of those ripples. Now if you have another material and a load of waves are approaching it, so this is the direction that the waves are coming in at, sometimes those waves can be reflected, which means they bounce back. Sometimes they can be absorbed, which actually means they're stopped, and sometimes they are transmitted through that material. But as they go through that material, certain things change. It might be that their wavelength decreases or their speed decreases as well. Now in the simple case, if we think about what happens to reflected light, and I've just got a mirror here, we can draw a mirror like this. So I've got the shiny side here, and this is the dull side. We can then draw our rays of light, which is maybe showing the direction that wave is travelling. So maybe this is a light wave, and then this is reflected. Now, this line here at 90 degrees to the surface is called the normal. And in this case, if we're maybe thinking about a ray of light, this would be the incident ray. So this is the angle of incidence. this is the reflected ray, so that's the angle of reflection. And these are always measured between the ray of the wave or the light and the normal. Now the next thing we can maybe consider is sound. Again, this is our longitudinal wave, and it has an approximate value of about 330 meters per second in air at ground level. Obviously that changes as you go higher, and it gets a lot quicker if you're looking at sound in a solid. Now the reason that sound travels is because we have vibrations in particles. These ones here maybe start to vibrate or oscillate backwards and forwards, and they pass their vibrations on and on. And what we have then is, in a sound wave, you have regions where we have the air which is compressed, and regions where the particles have separated, which is called rarefaction. And humans and all animals, we use our ears to hear things. So this is my diagram of the ear. Now you've got the air particles which are vibrating, and basically this is the ear canal here, and they then cause this part here to vibrate. So this is the eardrum, and this passes these vibrations onto the fluid here, which causes these bones to move, and then that then sends an electrical signal down this nerve here into the brain, which is when we then detect a sound. Now the thing is that this can only vibrate over a limited range of frequencies. For the human, it goes from 20 to 20,000 hertz. So anything above this, any sound waves which are higher than this, we can't detect. So sound waves that we can't hear have a frequency greater than 20 kilohertz. And this is what we then call ultrasound. Now with ultrasound, we can actually use this to look inside things that we can't see. Now a very simple example would be if you had a pipe and the pipe had a crack in it, maybe somewhere in that pipe. If you had a transducer here which sent down an ultrasound wave, the wave would travel down the pipe, and when it gets to a boundary, which is where two things meet or where there's a crack, what we then get is a partial reflection. So some of the wave might pass through, but some of the wave would bounce back. Now what we can do is we can actually record the time that the detector then works out when the signal is coming back. If we know the time it takes, and we also know how quickly these ultrasound waves actually travel through that material, we can then work out the distance, because the distance we can work out from S is equal to VT. Now the careful thing you've got to make sure is actually that's the distance to and from the obstruction, and so you'd have to divide that by 2 to find the actual distance from here to there. Now the same things work if we're looking at inside mummies' tummies, and we're looking at maybe scanning babies. Again, what we can do is, because these are completely safe, we get a partial reflection from the baby inside the mother, and that allows us to then actually build up a picture of what that baby looks like, and actually kind of check their kind of how they're getting on in terms of if they're developing properly, and also if it's a boy or a girl. Now another type of wave that we can look at are seismic waves, and these are things which happen when there's an earthquake or some massive movement underground. Okay, this is not a great circle, but this is supposed to be my picture of a cross-section of the Earth. And so maybe there was an earthquake at this point up here. What we'd then have two sorts of waves. We'd have our primary waves and our secondary waves. So these are called P waves and S waves. Now the P waves are longitudinal, and that means that they can travel through liquids and solids. But the S waves are transverse, and that means that they don't work going through liquids because of the way the particles move, so these can only go through the surface. Now the centre of the Earth is there's this kind of molten kind of region around here, and what that means is that S waves can basically travel through the mantle and the upper parts of the Earth, so this is maybe where we're detecting S waves, but P waves can actually travel straight through the middle, and they do get refracted slightly, but basically these P waves can travel from one side of the world to the other. And by detecting these waves, we can actually then work out, sort of looking backwards, at the structure of the centre of the Earth. So seismic waves often caused when parts of the Earth move and there's maybe some kind of earthquake. We detect the primary and secondary waves at the surface, but it's what they travel through beforehand and where they end up that then tells us about the structure of the Earth beneath us. But now let's look at the electromagnetic spectrum in a bit more detail. So the electromagnetic spectrum is a whole series of waves, and all of these travel at the same speed through a vacuum. This is also the speed of light, which is 300,000 meters per second. So that's pretty quick. And there are 7 main categories of waves that we're interested in. And so we go from radio at one end through to gamma at the other. So you've got radio waves, microwaves, infrared, which means below red. Then we have visible light, and because you've got infrared and then visible, that means we start with red waves, which are the longer wavelength, and then we go roll your biv to violet light at this end of the spectrum. We then go beyond violet into the ultraviolet. We then have X-rays and then gamma rays. And gamma rays are again this thing which are emitted by the nucleus of an atom. Now basically, as we go this way through the spectrum, what we find is that the wavelength lambda decreases, but also as we go along this way, the frequency increases. And what we find is that when you have higher frequency electromagnetic waves, they're going to be more dangerous. We can say they're more ionizing. And really from this point onwards, what we have is ionizing waves. Now what that means is that ultraviolet isn't great for you, X-rays are worse, and gamma is worst of all. So that as you have a higher frequency, the waves become a little bit more dangerous. So why is it that you need to know about this? It's because these have loads of uses. For example, if we think about radio, this is used for television and radio, so used for communication. We also use microwaves for communication, and this might include things like your mobile phone, but also we have satellite communication. And we can also use this to heat up food because it causes certain molecules to vibrate at the same frequency. So we can also use this for heating up food in your homes. When it comes to infrared, we can use this for heating because infrared is just a type of heat radiation. And we can also use it for night vision, so perhaps you have cameras that can see in the dark. Visible light, used all the time, including things like fibre optic communication. So that's how you get your broadband nice and fast. We then have ultraviolet, which is used for energy efficient lamps and also for sun tanning, so if you want to get bright orange. Running out of space here a little bit. Now X-ray and gamma, both really high frequency. These can be used for medical uses. So they can be used to actually scan the body to find out where something's gone wrong. Maybe using a conventional X-ray, maybe a CT scan, or maybe some radioactive tracer. But they can also be used to actually blast away at the damaged parts of the body to actually maybe reduce cancer, for example. So here are just some uses of different parts of the electromagnetic spectrum. Now something else that light does is it refracts. So refraction is when you have a wave and it meets a different medium, so it might be a different substance, and then it changes direction because it changes its speed. And you might get perhaps a glass block or a perspex block, and you shine a ray of light at a certain angle, and this hits the surface here, so this is my normal. What happens then is that this changes direction through the medium, and then when it comes out the other side, it then goes back into the original direction. So this is called refraction. And the reason for this is if we were to maybe zoom in on this part over here, where we had the waves hitting the surface, if we think about the wave fronts hitting that surface, one side of the wave is going to hit the surface before the other. And as it hits the surface and slows down, it does something a bit like this. So it starts to slow down on that side still moving. And then that means it all, as one, because effectively one side is slowing down before the other, it changes direction. Now that's maybe not so obvious, but if I put in this line here to show the direction of that wave, what we can see is as the wave slows down, it changes direction. The next thing I'm going to look at is lenses. Now there are two main sorts of lenses. We have lenses which are shaped like this, and we have lenses which are shaped like that. Now this type here that bulges in the middle is called convex, and the one that has a dip in the middle is called concave. Now this might be familiar. If you're short-sighted and you look at your glasses, they look a bit like this. If you're long-sighted, your lenses are slightly fatter in the middle. And these work by refracting light. So as light comes in, because it's slowing down, it changes direction, like we saw over here. And depending on the shape of the lens, we either make the light come together at a point, or the light splits apart. And we can use that when it comes to drawing ray diagrams. So for a concave lens, this is how we represent it on the diagram here. If you've got an object a long way away and we look at the rays of light that come from the top of the object through the lens, it goes through the focal point, and when rays of light cross over, we then see the image. So that's if you have a convex lens and you've got an object which is a long way away. If, however, the object is a lot closer, we still construct the ray diagram in the same way, but here the image is now formed behind the object, and it's actually made out of virtual rays, so what we see is a virtual image over here. This one is enlarged, and this is the way that a magnifying glass works. But with your concave lens, what we have is, again, if this is our object over here, the ray of light, when it goes through the lens, it actually then bends away from this principal axis over here. I've got videos that explain this in a lot more detail because it does take a while to actually get used to this. But basically, when you have a concave lens, the image that we see is smaller and it's a virtual image. And if we want to look at how the image size compares to the object, we can look at the magnification. I'd also like to look at colour, and we're thinking about colour in terms of the visible part of the spectrum over here. Now, each of these colours has its own frequency and wavelength, and they behave in a certain way as they may be going through either filters or maybe they're bouncing off a surface. Now, a green filter will only let green light through, and a red filter will only let red light through. That means if you put the two together, because no red or green light is going through, basically no light gets through at all. We can also see that by, if I have this green laser over here and I can shine the dot here, if I shine the green light at the green filter, all of that light just gets through. You can see that it just, even though it's hitting the filter, all of that light is getting through. If, however, I shine that green light at a red filter, it doesn't get through anymore, because what's happening is that the red filter is absorbing all of that green light. But if you had maybe a red object like this, why does it appear red? Well, because this object here is reflecting any red light. Now, white light that's landing all over this video at the moment, that's made up of all of the colours of the rainbow up here. But this thing here, it's absorbing all of the other colours, but it's reflecting the red light. This green block, on the other hand, that's absorbing all of the colours of light apart from green, which it's reflecting. Now, if you had a white object, it would be reflecting all of the colours. If you had a black object, it would be absorbing them all. And this brings us nicely onto a black body. Now, in physics, a perfect black body is something which absorbs all of the radiation landing on it. So that means all of the light, all of the infrared, it absorbs it all. It is also a perfect emitter, and that means that it gives out this radiation really quickly. And this then links back to the Earth. Because the Earth, if it's absorbing radiation, and there's going to be energy that we absorb that's transmitted from the sun, if we're absorbing more than we're emitting, then the temperature is going to start to increase. And this is a real issue in terms of global warming and climate change. And as our atmosphere is changing because of the different concentration of greenhouse gases, so things like methane and carbon dioxide, that means that it's harder for this extra energy to escape the Earth. So what we're finding at the moment is because the Earth is absorbing more energy than it's emitting, that means its temperature is very slowly rising. So on that bombshell, that is the end of the AQA waves topic. Just a very quick summary. And again, you can find videos that explain all of this in loads more detail at GCSE Physics online. Now, before we start looking at electromagnetism, let's just think about normal magnetism. So this is a bar magnet. It's got a north pole and a south pole. And there's a region surrounding this where a force acts on other magnets or maybe magnetic materials. And we can see that if we put this other magnet over here, something's going to happen, and it's the south end which is attracted to the north. So when you have unlike poles, they attract. If the two poles are the same, they repel. Now, for this magnet, the strongest field is going to be at the poles. And we can actually plot this using a small plotting compass, where when you put it on the table, you can see which way it lines up, and then you can actually then start to draw the field lines. But the field lines look a bit like this. So that's just a rough sketch. It's supposed to be symmetrical, and the field lines go from north to south. I'm just going to put some arrows on the diagram to show that. So this is the magnetic field around a simple bar magnet. Now, this is also the shape of the magnetic field around the Earth. And this is the reason why if you have a compass, if you're navigating, it always points to north. So the evidence that we have this magnetic iron core in the centre of the Earth is because of the magnetic field that we can experience and actually detect every day. But something really happens if you have a piece of wire and you connect it into a circuit so that there's a current flowing. What we then have is what we call an induced magnet. So just by having a current flowing in a conductor, we then have a magnetic field. Now, if we have a conductor like this, which is just a wire, then if we actually start to look at the field lines, so maybe we've got the current flowing in this direction. I'm just going to draw the field lines in green. What we have are these concentric circles that get more and more widely spaced as we actually draw that. And we can actually think about the direction of this by using our right hand rule. So if this is the direction of the current with my thumb, then my fingers point in the direction that field is going. So we have the field lines like this. I've just got an arrow to show the direction of that field. Now the thing is, if we had more wires, then we'd have a stronger magnetic field. And actually, if we had it coiled round into a coil like this, we'd have an even stronger magnetic field. Now this coil of wire here, which is a coil of wire that can carry a current, is called a solenoid. And if I was to draw a solenoid a bit like this, I could then draw the magnetic field lines through it. And actually what we find is in the middle we have these lines which are really close together, like this. And they also come around the side like that. In actual fact, this is the same shape as we have around a permanent magnet over here. But in the middle we have this dense magnetic field where all the field lines are really close together. Again, these can go from north to south. And so in a solenoid, what this behaves is when you put a current through it, this behaves a bit like a bar magnet. And that's incredibly useful for all sorts of devices. Now when you have a current and it's moving, this then causes there to be a magnetic field. And these three things are really closely linked to one another. So you have a current flowing, so there's a movement of electrons inside a wire, we cause a magnetic field. But what would happen if we had a magnetic field and a current flowed in that? What you then get is the third side of the triangle, you get the movement. And this is called the motor effect. So the motor effect is put to good use in motors. What we have inside this motor here is we have some permanent magnets. When the current starts to flow, we then get movement. And we can actually use something called Fleming's left-hand rule. Now for this, my first finger tells me the direction of the magnetic field. Now a magnetic field we actually give the symbol B to. My second finger tells me the direction of conventional current. And my first finger tells me the direction of the force that a conductor is going to experience, and therefore the direction it moves. So we can see that we've got from this triangle over here, we've got magnetic field, we've got current, and then my thumb is the force or the direction of that movement. So these three things are really closely linked. Now what this means is if you had just a single wire in a magnetic field, we could predict which way it's moving. So let's imagine we had the north end and the south end of a magnet like this. Between the two of them there's going to be a region where you have a magnetic field. I'm going to draw this in because we know that the magnetic field goes from north to south. Now this wire here is effectively coming out of the paper towards you. I've just drawn that with a dot. We can then use Fleming's left-hand rule to predict which way that wire would move. So first of all, my first finger is a magnetic field going from north to south like this. My second finger is a current, which is coming out of the paper. It's pretty awkward to do this. And my thumb is pointing up. So what we'd have here is the wire would move in this direction. Obviously we could turn that wire to go downwards by either reversing the direction of the magnets, or we could reverse the direction of that current. So effectively what we're doing there is if we were to reverse the direction of the magnetic field, this would happen and my thumb would point down. Really awkward to do. If you're in an exam and you see people starting to do this, there's probably a question about the motor effect and Fleming's left-hand rule. But how does a motor work? Well, effectively what you have is you've got a coil of wire, and some of the wire is coming, some of the current flows towards you, some of that current is flowing the other way, and what you then have is as soon as you pass a current, basically the piece of wire, some of it moves up, some of it moves down, and then you can use a thing called a split ring, and that allows you to then have electric current flowing always in the same direction inside that motor. We can also use an equation to do some calculations, and we can actually look at the size of the force on that conductor. And F is equal to B/I/L, where we measure our force in newtons, we measure our magnetic field in the Tesla, like the car, current in amps, and length in meters. Now, it's not just motors that use the motor effect, we can also use it in loudspeakers. Now, in a loudspeaker, you might have a very small circular magnet, like this, okay? And this is connected to maybe a large paper or cardboard cone. Okay, so you've got your magnet at the bottom. What you then do is you have a coil of wire that comes in and it goes around this several times. Okay, now what happens is that if you have a current flowing in one direction, you've got a current flowing, you've got a magnetic field in this permanent magnet down here. And what that means is that maybe when the current flows this way, the thing here moves up. If you then have the current flowing in the other direction, it moves down. And by varying very quickly which way the current is flowing, that causes the speaker to move up and down, which then causes a load of sound waves to be radiated from this. But this doesn't have to just be a motor. If we think about maybe moving this thing inside a magnetic field, what we're now doing is we are using this as a generator. So by moving this conductor inside a magnetic field, we induce a potential difference and therefore we induce a current. So a motor and a generator are very, very similar. Again, all we're doing now is completing, I guess, the other side of that triangle. So we can also think about the generator effect. So with the generator effect, if a conductor moves relative to a magnetic field, or the magnetic field around a conductor changes, then we induce a potential difference across the ends of the conductor. And this is, if this is then part of a complete circuit, we then have a current that flows. So how do you make this effect bigger? How do we get more electricity out of our generators? Well, one thing we can do is we can increase the size of the magnetic field. So you make the magnetic field bigger, it's going to cause a bigger voltage. You can also make it move quicker. So V is our velocity here, or speed. So we can move something quicker. And also we can have, if you had maybe a coil of wire which is turning inside the magnetic field, what you can do is you can have more turns. So this solenoid here has one coil of wire, but the amount of times that it goes round gives us a number of turns. So if you have more turns on the generator, that's going to cause there to be a bigger induced potential difference. Now, generators are really two sorts. We have things which are AC, so alternating current, and this is called an alternator. But you can also have ones which give a DC supply, and this is called a dynamo. And if we were to look at the output voltage with time, what we'd see is for an alternator, you'd get something that looks like this. Now, if you were to spin it quicker or you had a bigger magnetic field, what we'd then have is a higher voltage, but if it's spinning quicker, then we'd have more cycles per second. And the last thing we're going to look at is the transformer. Now, a transformer is really useful in the national grid because what it does is it allows us to change the current and potential difference in a different part of a circuit. Now, what we have here, this is our normal transformer. We have a primary coil and we have a secondary coil. So if this is where the electricity is maybe starting, this is our primary coil. It's got a number of turns and there's a different number of turns on the secondary coil. So what happens is that when you have an alternating current in this wire, this causes there to be an alternating magnetic field, like we saw with the solenoid up here, inside this iron core. So this iron core then becomes magnetized. And what we have is the magnetic field moves this way and then moves that way. What we then have is this iron core transmits that magnetic field to the secondary core. So inside this coil of wire, we then have a changing magnetic field. If you've got a changing magnetic field, which is effectively that magnetic field is moving, we then induce a potential difference. So we then have a potential difference in the secondary coil, which causes a current to flow. So that is the kind of bog standard average transformer that you need to know about for GCSE. So with this, we can think about the potential difference in the primary coil. We can think about the current in the primary coil and also the number of turns on the primary coil. And obviously we can do the same for the secondary. And what we find is that the potential difference increases in proportion to the number of turns from the primary to the secondary. So what we can say is that Vp over Vs is equal to Np over Ns. So imagine that had 5 turns and that had 10 turns. That means you might go from 5 volts to 10 volts. But when you increase that potential difference, we reduce the current. And the other equation we can say is that VPIP is equal to VSIS. So this is effectively power, remembering that power is equal to potential difference times current. If you've got a power coming in, it's the same as the power going out, and that means that the initial power on the primary coil is the same as the power on the secondary coil. Now on a step-up transformer, it steps up the potential difference, so that means there's a bigger number of turns on the secondary coil than the primary. If, however, you had a step-down transformer, you'd have a bigger number of turns on the primary than on the secondary. And what you have in the national grid is that you step up the potential difference when you leave the power station, so it's thousands and thousands of volts, and then you step it back down to eventually 230 volts for use in our homes. So that is a summary of AQA electromagnetism. It can get a little bit tricky at times. If you want to find out more detail about anything in this video, there will be videos at gcsephysicsonline.com. So this is revision of the AQA space physics topic. Now in the universe there are hundreds of millions of galaxies, and the Milky Way is the one that we're in. And in each of these galaxies there are different stars. And what I like to think about is our own solar system, which is surrounding our sun. So you have the sun over here, then we have Mercury, Venus, Earth and Mars. These are the smaller kind of rocky planets, and then further away from the sun we have the gas giants, Jupiter, Saturn, Uranus and Neptune. And to remember the order, if you need to, you've got S-U-N, so you start with the sun and you end with the sun. Now in addition to these 8 planets, what we have are a number of moons. So going around the Earth we have our natural satellite, our moon, but don't forget that these other planets as well, they have their own moons as well. So these moons are orbiting their planet, and we do have some other things which are orbiting the sun. For example, you've got comets, which maybe aren't round, but we have these kind of comets and asteroids, and maybe these have a more elliptical orbit around the sun. But where did our sun come from? Well, it started out in a nebula. Now, a nebula is just a massive cloud of dust and gas. And all of these particles, they're all attracted to one another due to the force of gravity. And what they do is when they come together, they lose some of their potential energy, and that's transferred to their kinetic energy store. And this then forms what we call a protostar. And eventually this protostar turns into what we call a main sequence star. And this is basically where the star is in its stable phase. It's going to spend about 95% of its life there. And basically what you have is there's an equilibrium between the fact that gravity is pulling everything in, and there's nuclear fusion happening, which is kind of pushing everything apart. And this is where the star's in equilibrium. It's not getting bigger or smaller. So that's the main sequence. And if we have a star a bit like our sun, so a sort of low to medium mass star, that's where it's going to spend most of its life. But at the end of its life, it starts to run out of fuel, the hydrogen that it's fusing into helium. And what happens then is it actually expands. It gets cooler, but it gets bigger. And then it becomes a red giant. Now, when it's a red giant, we're having fusion of heavier elements, but it gets to a point where it just runs out of fuel. And at that point, it then gets smaller and smaller and shrinks. Now, as it shrinks, the surface does get hotter. And this is basically where it kind of dies effectively, and it's very, very small, so it's called a dwarf. And because it's got the actual surface has got hotter, even though it's giving out less energy, this is what we call a white dwarf. And eventually, after billions and billions of years, this white dwarf is going to cool down to make a black dwarf. So this is the stellar evolution, what happens to a star like our sun through its lifetime. But we also have bigger stars as well. So again, if you have a bigger star, it's going to start in a dust cloud called a nebula. But this time, because there's more stuff that comes together, what we get is a bigger protostar. And a bigger protostar is going to make an even bigger main sequence star. Now this main sequence star, because it's bigger, there's more stuff, so there's a bigger force due to gravity pulling everything in. And that means that actually bigger stars burn through their fuel a lot quicker. They often burn brighter, so this is more of a whitey to even blue colour compared to the yellowy orangey colour of stars like our sun. So this main sequence star, it burns through its fuel really quickly, so it gets to the red giant stage really quickly as well. And then it becomes a red supergiant. And again, this is furiously burning fuel, and at the end of it, what happens is there's no more fuel, the force of gravity pulls everything in, and the outer parts of that star bounce off the very dense core that's remaining. And then there's this massive explosion, which, basically lights up a whole galaxy. This is called a supernova, and then one of two things can occur. basically whatever's left over, the core that's left, it's basically giving out a huge amount of energy and it's spinning really, really quickly. And effectively, all of the particles inside, because there's no fusion taking place, all of the electrons and protons have been pushed into each other to make neutrons. And it's a bit like a massive nucleus for an atom. So this one here is what we call a neutron star. But if the star is super big, then actually everything will just keep collapsing under gravity. There's no force that can actually cause this to not get any smaller. And what happens then is that all of this mass ends up shrinking into effectively no volume. Pretty weird stuff, but this is called a black hole. And these are absolutely fascinating. The strength of gravity is so much that not even light can escape. Now, we can't really actually directly see a black hole necessarily. We can maybe only see the effects that it has on things nearby. But there's no light being emitted, so we can't actually see light shining out of a black hole. Now, gravity is super important. Gravity is what's pulling everything together, so things heat up, and that allows fusion to take place. So fusion is the joining together of light nuclei, and this means that we start to create new elements. Although anything that's bigger than iron, because iron is the most stable element, anything which is bigger than iron, maybe the iron in your body at the moment, maybe any gold you have in your jewellery, that must have been created in a supernova. Now, when the supernova happens, it kind of distributes these elements throughout the universe, which then might end up making another nebula, and then that then forms maybe the star in the centre of a solar system, as well as the material for the planets. So you've been formed in one of these supernovas. Now, the other thing that gravity does is it allows all of these planets and all of the satellites to remain in orbit. Because if you have maybe a sun here in the middle, and you've got the Earth which is orbiting around it at a certain speed, there's a force of gravity that's pulling this in. And what this gravity is doing, it's a force that isn't changing the speed, but it's changing the direction. And this then means that things follow a circular path. That's supposed to be a circle there. But you can have things like this comet over here. Now, this can still have a stable kind of elliptical orbit around maybe a sun over here. But what happens here is that as it gets closer, because it's losing some of its potential energy that's been converted to the kinetic store, it moves slowly a long way away, then it travels really quickly as it goes near the sun, sort of slingshotted round, and then its velocity decreases again. So we can still have a stable elliptical orbit for objects like comets, but this is where they're travelling slowly a long way away from the star, and they travel a lot quicker when they get closer to it. Now, we've seen that stars have a lifetime, and actually what we find is that when we look at stars which are a long, long way away, we seem to see that actually some of the light that they emit seems to be stretched, and actually the universe is expanding. Now, if it's expanding now, that meant yesterday it was a little bit smaller, and the day before it was a bit smaller. And if we go far back enough in time, we find that actually there was a point when the whole universe had no dimensions. And this is the point that we call the Big Bang. Now, the Big Bang happened about 13.8 billion years ago. And at that point, all of space and all of time was created. It's very strange to think, but before the Big Bang, time didn't exist. So this started everything. So the evidence for the Big Bang is that when we look at light from stars, maybe this is what the light should be. When we look at light from distant stars, that light all appears to be stretched. Now, the wavelength has increased, and if you remember from your work on the electromagnetic spectrum, when you have a longer wavelength, we then have red light. So what we see is that things which are further away, there's something that we call redshift. And actually, when we look at different galaxies which are even further away, the further away the galaxy is, the bigger the redshift of that light. And that means that everything is expanding away from everything else in the universe, which meant at some point it must have all been in the same place. And there's some kind of clever physics we can do to actually work out that this is 13.8 billion years old. Now, in the last 20 years or so, we found that not only is the universe expanding, but the rate of expansion is getting faster and faster and faster. So we don't quite know exactly why that is. And that's the really interesting thing about science. We don't know all of the answers. Obviously, telescopes are getting better. We've got more people working on it. We've got things like LIGO looking at gravitational waves. Super, super exciting bits of physics. And it might be that there's dark matter or there's dark energy, which is driving this rapid inflation of the universe. But basically, This is just a quick bit of revision of a small amount of space physics, a super fascinating topic. So we've got the parts of the solar system, we've got evolution of low mass and high mass stars, as well as evidence for things like the Big Bang.